We're going to look at two different things here. The first thing we're going to look at is unsymmetric bending, and what I mean by that is when the moment is applied about some axis other than the principal axis, so at some angle from the principal axis. And it's pretty easy to deal with these things. Basically, you just resolve the moment into components, one along each of the principal axes that we have there, about this, about symmetry there, and then essentially you just do the flexure formula about each axis and add them together through superposition. These plus and minuses that I have here and here, the book follows one way. I find it just easier to look at the problem and recognize that, for example, this one is in tension, this side is in compression, and on this guy the bottom is in tension and the top is in compression. So when you're adding them together, you recognize, if I'm adding up in this upper right hand corner, you just recognize that it's in compression on each one of them and they're both negative values. So again, it's just a look at the picture, you break it into components, figure out based on what you're trying to, what part of the beam you're looking at, if I'm under compression or tension about either axis. The second thing we're going to talk about is a composite beam, and this is a beam that's constructed of multiple materials like I have here. So I have two separate materials, a less stiff and a stiff material there. And the way we do this is we basically transform it into a single material. Okay, and now the stiffer portion has to be widened so that it can carry an equivalent load. So effectively, because it's stiffer, if I'm going to make this all the less stiff material, then the stiffer material portion has to be wider so that it can hold the same amount of load that the stiff material held. Okay, so in our example here, again, E1 is greater than E2, right? 1 is the stiffer, 2 is the less stiff. Okay, so if I look at a little infinitesimal area right here, okay, the force is stress times area, where the stress due to Hooke's law is E times the strain times the area, dz dy. On the transformed piece here, everything's the same, but instead of dz, I have some value n dz, some integer that I'm, not necessarily integer, some constant that I'm multiplying that by, making it a little bit wider. Now, again, these two have to equal each other so that they have the same load, right? The same df, so it can hold the same amount. Okay, so equating these two df's, one on a transformed piece, one on the original piece, you get the following equation. Basically just equating these two things. Lots of things go away, and this basically, we get that value n that we're looking for, which is a ratio of the stiffnesses, the Young's modulus. Okay, and then I can find the new length of the stiff portion, which has now been transformed into the less stiff material, as B2 is n times B, where n again is that ratio of the Young's moduli. Okay, once I have this piece, I can find my neutral axis and find the stress in the less stiff material as I have here. Okay, once I found that, then I can transform into the stiff material, okay, by finding again the stress in the less stiff material, multiplying that times that value n to get the actual stress in the original material. Okay, there's an example of these composite beams. I recommend you looking at that. Might make more sense than walking you through this way. Okay, but again, the general idea is you take the two materials and transform it into one material, making the stiffer portion wider than the less stiff portion.